So in this video, what I would like you to do is to calculate this definite integral here and try it with pen and paper, and then come back and you can see a detailed solution, and I will also give you an additional related exercise. Okay, welcome back. Let's look at the solution. So here is our integral, and the first thing I want to notice is that the range of integration for this definite integral is such that x is going to be less than 1. And you know if x is less than 1 that the logarithm is negative, so therefore the entire integrand, x itself is positive, is 1 divided by something positive and divided by something negative, so overall it's going to be negative. So our integrand is negative, and we expect a negative result for this definite integral. Now, the integral may look a bit tricky for a moment, but if you think about it, it's easy and we can perform it by inspection. The reason being that the integrand is of the form 1 over x, which is the derivative of the logarithm, times the logarithm to the power of minus 1. Now, normally, if you have a derivative of a function times that function to a power, you just add 1 to the power and carry on that way. But if this is log of x to the minus 1, if you add 1, you would get log of x to the naught, a constant, and that's clearly wrong. So instead, the pattern that we recognize ought to be that this is going to be the logarithm of the thing which is raised to the power of minus 1. So we're going to have the logarithm of x. And I've just left a little bit of space here just to think to myself, if I differentiate this, do I get this? So if I differentiate the log of x, I get 1 over log of x, excellent, multiplied by the derivative of the argument, and that's going to give us the derivative of log, which is 1 over x. So this is perfect. I didn't need to leave the space there. If I differentiate that, I obtain this. Notice, and this is one of the key things in this video in my opinion, I'm using moduli here, and we need to have the modulus. The rule for the integral of 1 over x is that it is the log of the modulus of x. Okay, so now we're going to evaluate this at the upper limit and then subtract it, evaluate it at the lower limit. At the upper limit, we have the logarithm of 1 over e, which is e to the minus 1. And again, I'm saying logarithm of e to the minus 1, but we have moduli here. And then we subtract the same thing, but now evaluated at x is equal to 1 over e cubed, which is e to the minus 3. So the log of e to the minus 1, e to the minus 1 is positive, and the log of e to the minus 1 is minus 1. But this is a modulus, so it's actually the logarithm, effectively, of plus 1. And the logarithm of plus 1 vanishes. And then from the lower limit, we subtract, and it is the logarithm of e to the minus 3 is positive, its logarithm is minus 3. And in just the same way, we have a modulus, so this means the logarithm of plus 3. And the logarithm of plus 3 is going to be a little bit bigger than 1, because 3 is a little bit bigger than e, and logarithm of e is 1. And if you put it into a calculator, you'll see it's a number that's roughly 1.1. So we have 0 from here minus a number which I'm going to leave as log of 3 here, but it's about 1.1. So our answer for this definite integral is equal to minus the logarithm of 3, and that's roughly minus 1.1. So we see, as expected, the negative result. So it's negative, and that's something that should cheer us up. Okay, on the next slide, I'm going to give you a similar exercise to look at. So as an exercise to complete this video, what I would like you to do is to try to calculate this integral here, and the answer you should obtain is 2, and should you need it, I'll give a very brief solution on the next slide, but please do have a go with pen and paper before you look at the solution, or you're really not helping yourself. Okay, see you in a minute. Okay, if you've got 2, that's great, and if you haven't, or you're not quite sure, let's look at it on the next slide. So this is the integral that we want to find, and if we realise that this means 1 over x times log of x to the power of minus a half, we see that we have the derivative of the argument here. So we think we can do this by inspection. So we're just going to add 1 to the power, leave some space here. So log of x to the minus a half plus 1 is log of x to the half, the square root. So what happens if we differentiate this? We're going to pull out a factor of a half in front, and then reduce the power by 1. So we'll have the same argument, log of x to the minus a half, perfect. And then from the chain rule, we multiply by the derivative of the argument to the root, and the derivative of log of x is 1 over x. So that's almost exactly right, except we would produce a factor of a half if we differentiate this. There isn't a half here, and that's easily fixed. We just put a factor of 2 in front. So now we just evaluate this at the upper limit, and at the upper limit we're going to get 2 times the square root of the logarithm of e, and the logarithm of e is 1, minus 2 times the square root of the logarithm of 1, and the logarithm of 1 is, of course, 0. And this is the square root of 1, so therefore our answer for the integral is, as promised, 2. And it's worth realising that we do expect a positive answer, because over the range of integration, x is of course positive, and the logarithm of x is 0 or greater than 0. So we expect this to give a positive result, and indeed it does. It's worth noting that the integrand is actually diverging as x approaches 1 from above. So therefore what we have here is an improper integral, and if you'd like to be more careful, you could say that your lower limit was some constant, we could call it kappa, and then let's say we take the limit as kappa approaches 1 from above, but you will obtain exactly this result. This divergence from 1 over the square root of the logarithm of x is something which, although the graph is unbounded, the area is finite. And with that, I will stop this video.